Now that we have talked about the CFS scheduler, let's talk about another scheduling class, which is the real-time scheduler. And the real-time scheduler is basically used for real-time applications that are applications with constraints on when they should finish, applications with high priority. And there are two real-time scheduling policies implemented in Linux. One of them is SCHED5.0 and the other is SCHED-RR. They are both implemented in realtime.c, rt.c. You can this is your entry point for both of them, and they are not managed by the CFS at all. So CFS has nothing to do with real-time policies in the Linux kernel, but rather what you need is core.c and rt.c to basically run on using real-time scheduling. Uh, as any task that is basically set to SCHED5 or SCHED-RR will have a higher priority over any task that is scheduled like as SCHED normal. Because the real-time scheduling has a higher priority over the CFS scheduler, so that basically means that any task within that has been designated to run using one of these two policies will have a higher uh, priority. When a SCHED FIFO task becomes runnable, it will basically start running, and it will not leave the processor. It can run indefinitely unless it basically yields the processor, so voluntarily leaves the processor to wait for something, or it gets blocked on, for example, IO, needing to read something from memory or from disk, and then it will also get preempted until it acquires whatever it needs, but then it will rerun again. If there are any other, for example, sched normal tasks that are running on the processor at that time, they will all get preempted for the sched 5 or the sched rr processes, because they have real-time policy scheduling as their default scheduler. And then within the sched rr and sched FIFO policies, you will always have the priorities between the different uh, tasks based on the real-time priority number that we have discussed a bit earlier, that goes from 0 to 99 basically. This is used for the real-time scheduler to choose which task in the with which real-time task to run first. So something that is at priority 99 will run definitely before something that is at priority 50, for example. And as 99 takes precedence over 50, that means that 99 can run forever and thus can starve the whole system. So SCHED FIFO, if you have two or more SCHED FIFO tasks that are at the same priority level, then they will run in a round robin fashion between them. So the processor will basically, if you have like five different processes all at using SCHED FIFO and all having a priority of 99, then you will basically use round robin on them between them. So you will have you'll need to use some time slicing also. No, you will not need to use time slicing, but sorry, you will once one of them leaves, then the other will start in a round robin fashion. So SCHED-RR is identical to SCHED-FIFO, except that each process can run only until it exhausts a predetermined time slice. So you have time slicing here, and when you basically exhaust SCHED-RR task exhausts its time slice, then any other real-time process at its priority will is scheduled in a round-robin fashion. So round robin and FIFO are basically what we have been discussing in theory before. So they are just the very basic scheduling algorithms that we have talked about earlier. One thing to note also is that these are things that you would not want your system to run uh, all its processes, for example, using real-time scheduling, because that will basically starve your system, especially if you're using a FIFO, and will probably result in much worse experience. But in a car, for example, or in an aeroplane, you want your anti-skid system, you want your your braking system to function as fast as you can. So you'll have it as a sked FIFO. For example, these tasks you'll have scheduled as a sked FIFO. if you have an operating system for for a car, for example, or for an aeroplane even, because when you're landing or when you're taking off, then you'll have the crucial things at SCAT 5 because you do not want these things to be preempted for something like your air conditioning system, which is trying to maintain some good temperature inside the car. You do not want these to influence that because, sorry, you don't want the air conditioning to influence these cr- critical uh, applications, because these critical applications can mean that you die, while the air conditioning will just make you feel better before you die if you schedule it before the brake system. There are two kinds of real-time systems. One of them is soft real-time and one is hard real-time. And there is a large body of work. There is a huge theory behind real-time systems. It's typically studied between computing science and control theory. So you find that, for example, some of the very top people in real-time systems in the world reside in the Department of Automatic Control in Lund. Some are in the also computing science department at Uppsala, which is not called computing science; it's called information technology or something. So I mean, real-time systems theory is studied in different contexts. And in soft real-time systems, you basically do your best. You do not give guarantees, but you do your best to basically finish some tasks within some given time frame. So, for example, you say that my braking system will if hopefully work most of the time in 100 in less than 100 milliseconds, okay, but you do not give a guarantee, so it's not hard deadline, so it can take 105, it can take 120, it can take 200 in some extreme cases. And then you, in soft real-time systems theory, you will actually try to establish bounds on how long things will run, and how to improve these by improving the scheduling or the optimization of the system. In hard real-time systems, if you say that things will run in less than 100 milliseconds, then it will run in less than 100 milliseconds. And obviously, this is very hard to achieve, and that would require also, again, a lot of theory and a lot of studies on how to achieve these things in terms of scheduling and in terms of the errors in the measurements and so on and so forth. The real-time priorities in Linux are set using a range inclusive from 0 to max real-time priority. That this is basically something that you declare in your scheduler, minus 1. So that's the why you have from 0 to 99, because the default of max RT perio is 100, because then it gives you 100 priorities. Now, given all what I have said before, this is what you would need to actually do assignment 2. I hope that you have figured that out already. But these are the system, a few system calls that you can use to change the scheduling class for a process that you're running. So set scheduler will set a process's scheduling policy, and if you read through the man pages of this syscall, you will see what are the different parameters that you can pass to it. But sched normal, sched FIFO, sched RR are among these. You can set the parameters for the real-time priority, because right now it's set and I mean yeah, read the man pages, and you can get these parameters. You can get you can get the maximum priority of real time, and you can get the minimum real time priority also using sched get priority min. You can schedule an interval for round robin. So if you say, for example, that I'm gonna run it for 1 second or something, you can do that. Uh, no, sorry, you can get it. I think you can set it also. I think there is something also with which you can set the interval, but I might be wrong there. And scheduler set affinity is something that you would use to basically indicate to the kernel that this process should run on this CPU only. So if you have multiple cores and you do not want your applications, because in a normal case, then your tasks or your application will be jumping between different cores. So if you want to disable that, you can use the sched set affinity to basically make things work in such a way that they run always on the same core, or run always on the same two cores, or something along these lines, which can be helpful if you really understand the cache behavior of your system, you might actually be able to achieve a lot of speed up and a lot of performance gains by just using set affinity, or to do some temporal, basically, in place optimizations of your threads. With this, I conclude this lecture. See you all tomorrow. Tomorrow's lecture will be in the lab, and I will update you on a few things. I will also help you a bit with how to store things to a file system in your LKM. Thank you, and see you tomorrow.